Welcome to the channel where we talk about physics, math, and computer science. This video is a small follow-up on a couple of statements that I made in the previous videos in which we discussed quantum search algorithm. In the first video on quantum search algorithm, I said that when doing an exhaustive search over n elements, we need to examine the search space on average n over 2 times. In other words, on average, we have to check half of the elements before we find the solution. In the second video on quantum search algorithm, I said that when doing an exhaustive search over 4 elements, we need to check the search space on average 2.25 times. This is very close to half of those 4 elements, but one can still wonder if there is a contradiction in those two videos. The goal of this video is to show that there is no contradiction there, and I will do it by deriving an exact expression for the expectation value of the number of elements that need to be checked in order to solve an exhaustive search problem.
Let's define an exhaustive search problem. Let's assume that we have an unstructured search space of n elements, and let's assume that there exists exactly one solution, which we will mark as S. The goal of the search is to determine the location or the index of the solution S. So let's introduce index I and index all elements from 1 to n. So this element will have index 2, n minus 1 over here, n minus 2, and we assign index is to the solution. We will consider the search problem solved once we know the numerical value of the index is. And by the way, we can always index elements randomly. We just then will follow the index increment until we find the solution. And just a reminder, the unstructured search space means that there is no alternatives to a brute force search approach when we examine elements one by one until we find a solution. So the goal of this video is to figure out how many times on average we have to examine the search space before we find the solution S. So let's introduce a random variable k, which will be the number of examinations of the search space, or the number of checks we need to do to determine or to find the value of is. So we write the number of checks to find is. So this is a definition of a discrete random variable, and we need to find the average value of this random variable. In other words, we need to find the expectation value of k. And the expectation value, by the definition, equal to the sum of k multiplied by the probability mass function pk of this random variable. Before we determine what the probability mass function look like, let's find out what is the range that k can take. The minimum value of k will be equal to 1. And this is because if we are very lucky, then the first element we will examine will happen to be a solution. So k min is equal to 1. And the maximum number of elements, or the maximum number of examination of the search space that we have to do is equal to n minus 1. So k max is equal to n minus 1. And it is n minus 1 rather than n because we know that there exists exactly one solution. And if by the time when we reach index n minus 1 and looked at that element, we solve the search problem regardless of whether the solution is at that location or not. If it is there, then the index is is equal to n minus 1. And if it is not there, then we know that the index is must be n. And this is because there exists exactly one solution. So we never have to actually open or examine the last element in order to find out what index the solution has. So the sum over here has to be done from 1 to n minus 1. Now let's determine what is the probability mass function pk. Just a reminder, the probability mass function is probability. It gives the probability of each numerical value that the random variable can take. So let's look at the random variable k values from 1 to n minus 1, sorry, n minus 2. In this case, there is only one slot out of all the n elements where the k will have a number from, will have a value from this range. So the probability of that is therefore 1 over n, because there are total n slots. The probability of occupying a single slot is 1 over n. When it comes to value of k equal to n minus 1, there are two spots that solution can occupy in order for k to be equal to that number. So the probability of k equal to n minus 1 is 2 over n. And it is 0 for any other k, and if we assume that it is positive, then we can write it greater or equal to n. And this is a probability mass function for random variable k. We can do a sanity check and check a normalization requirement. A probability mass function has to satisfy this requirement. So the sum of all probabilities has to come up to 1. And we can actually check that by noting that there are n minus 2 values of k that has probability of 1 over n. And there is one value of k that has probability of 2 over n. 2 over n. And indeed, this is equal to 1. The normalization requirement is satisfied, and therefore, in order to find the average number of examinations of the search space, we just have to plug in the probability mass function pk into this expression for the expectation value of k. Let's do that. Let's work out the expectation value of k. Since we know the probability mass function pk, we can expand this sum in the following form. For the k equal to 1, the probability is 1 over n. For the k equal to, the probability is also 1 over n. And all the way down to k equal n minus 2, the probability is 1 over n. For the last value of k, n minus 1, the probability is 2 over n. We can take 1 over n outside of the brackets, and in the brackets we'll get the following series: 1 plus 2 plus n minus 2. And note that we have n minus 1 twice here, so we'll write it separately. N minus 1 plus n minus 1. Here we will note that we are dealing with the sum of consecutive numbers from 1 to n, and it is equal to n times n plus 1 divided by 2. So we can shorten this expression and write 1 over n, and in the brackets we'll get n times n plus 1 divided by 2 minus 1. And we can rewrite it a little bit, and finally we get the following expression for the k mean, the average number of checks that we need to do in order to solve the exhaustive search problem. for the search space of the size n is equal to n plus 1 divided by 2 minus 1 over n. Let's take a look at the couple of properties of this expression. First, let's take a look at large n's. When n is much greater than 1, we can plug a very large number into the formula above, and we will see that the number of times we need to examine the search space is approaching n over 2. And this is in agreement with our intuition, because, for example, we would expect to open about half of the card deck if we are looking for a particular card in the deck. For small n's, for example, for n equal 1, the number of times we need to examine the search space is equal to 1 plus 1 divided by 2 minus 1 over 1. This is equal to 0. And this is common sense, because if we have one element in the search space and we are told that there exists exactly one solution, we don't need to actually open the element. We know that the given element is the solution, and the index of that solution is 1. For n equal 2, the number of times we need to check the search space on average is equal to 2 plus 1 divided by 2 minus 1 over 2. And this is equal to 1. Again, makes perfect sense, because if there are two elements and we know that there exists exactly one solution, we can open the very first element, and if it is the solution, then the index of the solution is 1. If it is not the solution, we don't need to open the second element. We know that the index of the solution is 2. And finally, the case when n equal to 4. This is the case that motivated me to actually make this video, because in one of the videos on the quantum search, I said that for the search space of 4 elements, classically, we would need to examine the search space on average 2.25 times. And let's see if that's actually true. We will plug 4 into the formula and get 4 plus 1 divided by 2 minus 1 over 4. This is equal to 2 plus 1/2 minus 1/4. And this is equal to 2.25. So there is no disagreement or contradiction between situations when in the search over a large number of elements, we have to examine the search space about n over 2 times. And for the situation when n is equal to 4, we have to examine the search space on average 2.25 times.